Well, good morning. It's going to be another little 6-minute segment. What we're going to be discussing today, not going to be using chalkboards or anything, but this is for math-oriented people who really want to see a measurement system that can be put into play. And this is also for a professor I had at the University of Texas. His name was Gunn, G-U-N-N, as I recall he spelled it. And he challenged his students to come up with an explanation for why math, when you graph it, why it looks like a staircase. So for Mr. Gunn, and I hope that he came up with a system which made him feel comfortable in explain the stair step to heaven approach to math, that when you do math, especially calculus, it's going to look like your points are going to be graphed as a stair step: over 1, up 1, over 2, up 2, over 3, up 3, or something like that, depending on what kind of math you're going to do, what kind of calculus. And what we're going to call this segment, of course, is stair step to heaven for mathematicians. Now what Mr. Gunn was looking for was that trying to explain why the fundamentals of math would be based on such an observation, why we would tend to see, as opposed to a trig, a curving line, why we would see math tends to calculate things in this over 1, up 1, over 2, up, like a stair step, when you plot these graph points and everything. And what we're going to explain is what would be the fundamental observation in the nature of our universe, the fundamental laws, Newton's 1 and 2 laws, and Galileo's observation, and how did all this come to about? Well, first of all, let's give Galileo all of the credit. He wasn't too interested in math. He was a practical person and had not gone as far into math as Newton took this. But Galileo, as we recall, rolled bowling balls down ramps, you could call it, and from this formulated some interesting observations, of which, of course, inverse square is the derivative. Now, Newton took this, and of course, laying in his bed, sickly there for a while, he visualized an apple falling as opposed to a ball rolling. And once he did that, and this is where he kind of probably has it a little over the Polish guy who also worked with calculus and came up with the same formulation, mode or model, we could say, is that once he combined these two, it was easily seen, and was that Haley? I guess it worked with him. I'll have to look it up. That's history. Once he combined those two, instead of a ball rolling, but an apple falling, and this inverse square, if that was a fundamental of the workings of our universe, that's what we wanted to measure. That's what we wanted to do. And of course, the formulation of gravity for the people who are interested in since Copernicus' time into the heavens and everything, he formulated this calculus based on those rolling balls. And as opposed to a ball rolling, an apple falling, with this inverse square. That is, as you half your distance, you reduce the effect of whatever was causing you to move that distance by 3/4 or a quarter. It's like inverse square. Every time you increase your distance from Earth, you drop the effect of gravity by so many units, or every time you get closer to the Earth, you will increase the overall effect of, in this case, gravity by so many units. Inverse square. You double up, whether you move towards or you reduce that amount if you move away from the effect. And if you do this experiment, that Galileo did, you're going to wonder how the hell he came up with this. But right away, you'll see that as that ball leaves the end of the ramp, it's going to roll so far on flat ground. And the less you raise, or the more you reduce the ramp, the shorter the roll will be. Well, there you go, inverse square. You can extrapolate the events in relationship to how high you put the ramp or how low you move it. And this is going to roll throughout our physics. Now, the reason inverse square in math, calculus, go in this stair step is that this doesn't have a curve to it, okay? But yet everything else in the universe is curving. So we have this problem with math, especially with calculus, and which Trig tries to help to solve and stuff like this, is that we know that a ball or something moving through space is not, as we view it, is moving in a curving line, and not in this 1 over 2 back or 2 forward or something. It's not moving in this stair step line. So why would math, which is supposed to be a perfect example of the forces, the laws of nature, why would it be difficult to explain this effect when one is taking a look at this? How could this be? Well, the reason this is because although the math is a perfect solution and everything, we're Galileo and Newton were working off the ramp and the rolling balls. So therefore, the math is going, we're thinking that it's not a true prediction, but it is, because what inverse square is doing is not giving us a curve by measurement. It's giving us precession, the events of precession as an item that is in spin will precess. And now if we think of this mathematical model is reflecting this, that you're going to hit an object with force, it's going to move to the right. It moves in a straight line, or what we would call a straight line is what we want to, pretty much what we want to do. Now, our time is up on this, but let's just go ahead and surmise right now that with inverse square, with our math, with calculus, with all of these events, you are getting this 1 over, 1 out, 1 over, 1 out. You are getting a stair step because what we are measuring is application of force to a spinning body that's going to precess. And when you look at it like this, if you have this object rotating around you and you hit it with force, or whatever frequency at which you're hitting it with force, you're only going to be moving at distances right or left 90 degrees to the application of force. So therefore, you are getting this on again, off again, start and stop. You're getting this event. And it also explains why Newton had a feeling that there must be an inertia. Well, the inertia point, of course, is the axis of plane. That would be our inertia. In that the inertia is this line of precession that it wants to maintain. But all of a sudden, the spinning object gets hit again. So now it is changed from that inertia point to another 90 degree. So we're going to explain those two items, okay? Sorry about the limited time. But, that's YouTube. Bye-bye.